morning, everyone. So we start this lecture with the first lecture on multivariate time series. So this chapter or this unit means the lecture which I'm going to deliver a couple of lectures on this topic is basically I'll be using two books. One is this multivariate time series with R and financial applications, and another one which I don't have it here, but I can. It is mentioned in the syllabus. Luke Fold. That's another book by Luke Fold. Introduction to Multivariate Time Series. So the question here is, what is multivariate time series? So what we have learned in the previous course, in the time series course, you almost all the discussion, not almost all the discussion, all the discussion for that matter, is based on a particular time series. Like I'll be taking only one series, it's univariate, and then try to obtain, this series is being observed at different time points. And now we are trying to see how to model, how to do the forecasting, etc. This is what we have learned. Now, in this particular unit or in this particular section, we are going to observe a vector value time series, because it is not enough to always deal with the univariate time series. For example, there may be correlation between different variables, or there may be association between different variables which are being observed at the same time. For example, suppose income, investment, consumption. You are observing these three: income, investment, and consumption. You know that actually, income, from that you also consume and you also invest. So these are related basically. So I can't really have one series only on consumption. Of course, you can have it, but then it is not complete in that respect. Similarly, I may want to talk about M3 and GDP. M3 is the broad money, which includes cash in hand and time deposits, etc. So M3, including fixed deposit. This is now this particular, they may be correlated, so that's why we are considering them together. Now, not only now in this case, one of the important thing that you see, there is a serial dependence between components XIT. A serial dependence XIT1, XIT2. That means GDP at two different time points may be dependent. At the same time, uh, GDP at one particular time point could be depending on M3, maybe at the same time point or maybe at another time point. So lag can also have a dependence. So what happens that because of this, we need to consider them together. Now, what happened the moment that we say multivariate, in univariate itself, you have, depending on the number of orders, your parameter increases. Like in a ARP, you have P parameters for the coefficients, and then there is a variance parameter. But now when you talk about multivariate, what happened that this exponentially increases the number of parameters. Because you have a vector here, so the k-dimensional here, and if there are several lags are depending on the time point t, so the parameter over there is turning out to be a matrix. So in the sense that you will have to have a k by k matrix associated with that. Otherwise, the matrix multiplication doesn't match. What I mean to say that you have several parameters to handle in this situation. So to one major issue in this context is dimensionality, that number of parameters increases. And another major issue is that, identifiability, because, when you have more number of parameters, there is a problem of identifiability. Because two probability mechanism looks alike, so you are unable to distinguish between them. So that is what basically the identifiability. Now these are the two major issues, so we'll see how this is addressed in many cases. So here the objective is to study the relationship between variables to improve the accuracy of the prediction. Now look at this as an example. Is a multivariate time series with US quarterly real GDP, GDP in logarithm, So this is quarterly growth, not the absolute value. It is growth. Growth means GDP at time t minus GDP at t minus 1 divided by GDP at t minus 1. That's what generally the growth. Uh, then you have change rate. This is basic, and the change series of unemployment. So this is basically the unemployment rate. These are seasonally adjusted. This is, of course, this is about GDP only. I mean, like somehow I didn't have the unemployment rate here. Uh, so this is like GDP growth. Yeah, this is this only unemployment only. I mean, like this is basically showing this. So the growth in the unemployment rate. So now, what in this context also one can define the concepts like stationarity, causality, invertibility, etc. So we define that first before getting into any computations or calculations. So weak stationarity is basically, we know that the mean and variance are independent of time, and the covariance is basically a function of time difference. So the same thing here also, but now what happens that mean is actually a vector because your variable is a vector. So you have to talk about this, the mean vector. Similarly, the covariance is actually, this is a covariance that should be free from time. So this is free from time. So this is what weak stationarity is all about. Once it is free from time, if you are considering a difference, it is just the time doesn't matter, what the lag matters. So that is automatically comes over here. Now strict stationarity can be defined similar to the univariate case by considering joint distributions of this. So you have the same kind of definition, but I have now the vector. So x1 t, x2 t, etc. xkt. And then x1 t plus h, x2 t plus h, sk plus h. These two vectors should have the identical distributions. Then we say that these are strictly stationary. Now, there is a terminology problem here. Some people call it as linearity. Basically, this is causality, that what we have learned in the univariate case. So if xt, you can represent it like this. Now, xt is a vector, and this is now, it's a vector, white noise with mean 0 and a covariance matrix sigma z. So this is earlier, I mean, we were discussing it as a white noise with mean 0 and variance sigma square. That was univariate case. Now this is a vector valued. So the mean is 0 and 0 vector and positive definite covariance matrix sigma z. So sigma square replaces this particular one. Now, if you can represent it like this, of course, you can be 0 also sometimes. Now, when you represent like this, these are not just real numbers or not even vectors, these are matrices. Because if it's a vector, this order doesn't match. So you can't really get this vector out of this if you multiply by a vector. So it means that you have to have, because if you want to get a vector here, this multiplication has to be with a matrix. So this is psi i's are matrices. So this is psi I is a k by k constant matrix. Okay, and so if you have this representation with these conditions satisfied, now for the linear xt to be stationary, the coefficient matrices should satisfy this condition. What we have in the univariate case, we used to call it as absolute summability. But now that absolute summability is meaningful in the case of univariate case, but not here, because what you have is matrices. So the absolute summability means some kind of norm you need to sum. So there are different norms that we can consider. Norm means norm of a matrix. Now it actually, matrix is basically, if I have a k by k matrix, you're talking about a k by k dimension or k square dimension, and from that you are mapping that to a single number, and that's what the norm. Like determinant is a norm because whatever dimension is, you're mapping that to a single number. So this is another norm what we consider here. Determinant denotes a norm of the matrix A. If I double line, single line we used to call it for determinant, double line is for the norm of the matrix. So for example, Frobenius norm, that is another one type of norm which is more popularly used in matrix algebra. So this is called Frobenius norm, is nothing but a square root of trace of a prime. So it is like square root of trace of psi I prime. That's what the Frobenius norm. Now we know that we have some condition. This absolute series is summable, then the nth term should go to 0. I mean, that's a pure mathematics analysis thing. So I can have, this should happen here also. That's very clear, because if each of them doesn't go to 0, the sum will not be finite, it will be infinite. So naturally, when you have a convergent series, the nth term should go to 0, which we have learned in even BSc. So that happens in this case also. But you see, you are not talking about real sequences, you are talking about matrices. And then these terms are nothing but the norms of that matrix. Now, invertibility is, I have written in a slightly different way, but it exactly what you are saying, that you can write zt in terms of the past values of xt. You can take it on this side. So zt, or this also can be taken on that side. So zt can be written as the past values, or the current and past values of x explicitly. Then we say that this is invertible. We have learned these definitions. Only thing is that now you are talking in terms of vectors. So in this case, these are matrices. See, these are not real numbers, unlike in the earlier case. These are matrices. So you see that this is what I said. The parameter size exponentially increases when you deal with matrix or vector valued time series, whereas univariate case, that's not the case. So that is where the identifiability and more parameters, the over parameterization problem actually comes in this case. Now, example, we know all AR models are invertible, whereas MA models are not invertible. We have to check that. By default, they are not. Similarly, AR models are causal, linear, and AR models, MA models are, so AR model invertibility is guaranteed, but causality is not guaranteed. MA model causality is guaranteed, but invertibility is not guaranteed. We know that from the univariate case. Exactly same thing hold in the multivariate case. Only thing is that now these are matrices. Okay. Now let's define covariance matrix. So we have basically what the main difference here. You have covariances of a single series with different time points. So I have single series means one component of the series, like GDP. So GDP at time t is related to GDP at time t minus 1 or t minus j for any j. Similarly, GDP is also having a correlation with M3. So M3 at time t could be related to GDP at time t minus j. That is possible. So in such a case, what we have is this matrix, a matrix that you get, whose diagonal entries are basically the covariances corresponding to, or covariance series corresponding to the individual series in the vector, and the off diagonal entries are nothing but cross covariances. So the diagonal elements are autocovariance functions of the univariate series, like this, and the off diagonal elements are cross covariances like xit, xjt plus h. Okay, so gamma ij tt plus h is covariance between xit and xjt plus h, whereas gamma ii is the ith unit or ith component of the vector, its covariance function, which we have learned in the univariate case in the last course. Okay, now if you look at the covariance matrix, you have this relationship. Covariance function is positive, so you have this relationship. But what happens when you actually get into the matrix? Because now that, the positive, negative in this case is because these are real numbers. This one, I'm talking about this one. But that, what is the case with this matrix? Because the covariance matrix, so you can see that little computation, you can see that gamma h is equal to gamma minus h prime, because a matrix, no? So how do you prove that? So gamma h by definition it is this, xt plus h. Well, some people take t and t minus h. I am consistent with t and t plus h, so I am using this notation. So you have this definition for the gamma h, and now because of stationarity, I am assuming stationarity. That's why we are discussing this. Assuming stationarity, You change this t to t minus h, so naturally this will be changing to t. So I have this. Okay. Now we know that A prime of prime is A. So I can write this matrix as prime of this something, right? The prime of this one will give me this. So I'll write like in that fashion. So the prime of this will give me this. Now, once you have this, what you have here is this. So the prime of this is this. So I'll be able to see that, now the covariance matrix, what is happening is that this prime is essentially same as this quantity itself. So what is that you are getting here is t minus mu t minus h. So this is pretty simple because prime of prime you get t minus mu, and this is t minus mu prime. So I have this. So in the next step, I'm just repeating this. This t minus h, actually this one prime is missing here. That prime you have to write. I'm sorry, there is a prime missing here. This bracket and this prime. So here what I'm doing is this is the definition, and this t minus h I am rewriting it as t plus of minus h. So this quantity will give me gamma of minus h. Okay, and there is a bracket and prime. I told you that I missed that bracket and prime here, which I will correct it. So that bracket and prime, so this I will get it as gamma minus h prime, or this is called gamma of minus h prime. So unlike, the main difference here is, unlike in the case of univariate stationary time series for which autocovariances of lag h and lag minus h are identical, like this, these are identical. But here they are not identical. Because gamma h is not equal to gamma of minus h, whereas gamma h is equal to gamma of minus h prime. Okay. Let me repeat that I missed this bracket and a dash here to write when I write. So I have to do that. Okay, then only all these things are correct. So this is one important point. Now, once you define this correlation covariance matrix like this, you can divide by gamma 1, gamma 0, 0, etc. And then you can get the corresponding correlation matrix. So because you see, this is how you define the correlation. Gamma ijh by gamma ii0 gamma jj0 to the power of half will give you gamma rho ijh. So define like that. Once you define like that, then you will get this thing is to be the correlation matrix. So this is called the autocorrelation matrix associated with the xt vector process. Now I want to show you some of the calculation or computations related to this. So I'm demonstrating an example. So this, in this example, what we are trying to, I'm trying to show this. There is a series like xt is a two-variate, so k equal to 2 in this case, two-variate vector valued process. Now first component is zt itself, and second component is a moving average, zt plus theta zt minus 10. Z is our white noise, so I have a vector valued process. Now I have asked you to compute all these matrices. The covariance matrices of lag 0, which is gamma itself, lag minus 10, lag plus 10. This is because I want to show that this is actually the transpose of this. Similarly, the correlation matrix, autocorrelation matrix, R minus 10, R plus 10, and R0. So let us do the computation one by one in this case. So I'm now going to change this to I'm going to change this to the whiteboard. So let's look at this. So here I have the process is basically what is this process? I'm going to write it here. This is changed. Sorry. So I have a process. This is my xt, right? Plus theta zt minus 10. So here you can see that mu equal to 0 here, the 0 vector. So I have to compute gamma 0, which is expected value of zt plus theta zt minus 10, and then I have zt this is basically xt prime. Okay, so this is my okay. Now you can do this calculation. So what happens? This is zt square, and this is zt is what is given? Zt as white noise 0, 1. Okay, so so this now you multiply, so that's why you get a matrix. So zt square, which is 1, and this you multiply, you get 1, and this is 0. This you multiply, you get 1, and this is 0. Z's are white noise, so whenever the lag is different, you get 0. And in this case, 1 plus theta square. Okay, so this is the matrix gamma 0. Okay, now let's compute gamma of minus 10. So what is gamma of minus 10? Which is basically expected value of zt okay, and this will be zt minus 10 and zt minus 10 plus theta zt minus 20. Okay, so now we can see that this is 0, this is also 0, this is theta, because this will be 1, this is 0, and this is 0, this is 0, this is theta, and this is 0. Okay, so my answer is this 0 0 theta theta. Let's compute gamma of 10 in this case, and I just want to see whether your claim is correct. So gamma of 10 is, I am doing it only for because of the first one, rest of the things you should do. zt plus theta zt minus 10. Okay, and here it is plus 10, so this will be zt plus 10, and here sorry, zt plus 10 plus theta zt plus this is sorry, I think I made a mistake. You are actually subtracting, so zt plus 10 I have to subtract 10, so that will be zt. Okay, right. So what is that you are going to get? This when you multiply z, this is 0, this is 0, and this you get theta. Okay, so you get theta. This you multiply, this is 0, all are 0. This you multiply z, this is 0, this is theta, and this is 0, because t minus 10 t plus 10 are different, and this is theta, this is also different, so the only contribution is theta. So now you can see that this is gamma of minus 10 prime, because that you take the transpose of that, that is this. So this is, I mean, we can see that gamma of 10 is equal to gamma of minus 10 prime. So this is how, this is a simple example, but you can, in almost all cases, it is going to be like this. Now I want you to actually compute, let's compute R, R0 and R minus 10. So I would like to compute R minus 10 in this case. So what is R minus 10? So we have this, actually this gamma 0 here. I mean like, gamma minus 10, 0, theta, 0, 0, theta, theta. And then you have to simply divide it by the square root of the variance. Okay. So this will be 0. You can compute even otherwise 0 is theta upon 1 plus theta square to the power of 1 half theta upon 1 plus theta square. What is 1 half that you get, because these two components are there, so this you have to actually evaluate. See this, told you R is row 0, 0, row 1, 0, 1. So between them, what is the covariance that you have to compute? So, and then square root of multiplication of that. So that leads to this particular thing, matrix. And similarly, you can also get R10. So this I am going to ask you to verify. Okay. So how do you verify? I mean, we have seen the formula. I mean, you have to just use the formula, and I have given you the components. So gamma 0 I have shown you. So similarly, R10 is different, because this will give me 0, 0, theta upon 1 plus theta square, and theta upon 1 plus theta square. So you can see that this is R minus 10 prime. See, when I ask you to compute this quantity, you don't have to do this exercise showing that. That I am just showing you because first of we are doing one example, so you should understand that this is nothing but the transpose of this. So similarly, you can also compute R minus 10, R0. So you can see in this case R0. So R0 will be different. Now in this case R0 is going to be 1. Sorry. Okay, so in this case, this is 1, and you get 1 by 1 plus theta square to the power of 1 half, and here also you get 1 by 1 plus theta square to the power of 1 half, and 1 here. So how do you get this? You see, we have actually, if you see, I have this matrix. So you put h equal to 0, and you can just compute them in this particular case. Okay, you need to do that exercise because you already know these things in the univariate case. So we can simply compute them in this particular case. Okay, so this is what the computation associated with. Of course, you can see that this is pretty difficult even in the case of bivariate, with a very simple structure where zt is and zt plus theta. So you can imagine how this complex this is going to be in various cases. But however, we have to learn complex things. So that's where now I have two exercises here which you have to work out. So this is one bivariate again, and this is the model now. The second one is like, zt, x1t is zt, whereas there are no past values of x1t, And the x2t is basically oh, this is typing is actually a problem. X2t is, this is x2t minus 1, not xt minus 1 2. X2t minus 1. I'm sorry. So there are two mistakes that I need to correct. X2t minus 1. Okay. Plus zt. X2t is equal to x2t minus 1 plus zt. So that's actually a phi x2t minus 1. So it is an AR kind of model. So this is an AR structure for this component, and this component is already a white noise structure. Now what is required? You need to compute all these things. Okay. Similarly, in this case also, here also I think there is some typing problem because I used t in the second place. So here x1t is phi x1t minus 1. Okay, so the past time point of this component. So you should read this as 1t minus 1, not t minus 1 1. In fact, in this case as well as in this case, there is a typing error. This should be 2t minus 1 and this should be 1t minus 1. Okay, that means the previous value of this particular series. And x2t is actually a moving average zt plus theta zt minus 1. So this is x2t. Now what is required is that you need to compute these quantities. Okay, so I think with this, what you need to learn today, we have introduced what is a multivariate time series, what are the important problems in that. The problems are basically because of more number of parameters and identification problem. And then we have seen what is the mean, what is the variance, what is the autocovariance, sorry, what is autocovariance, what is autocorrelation, and we have also seen what is meant by stationarity, weak, strict, linearity, causality, and invertibility. That's it. Thank you.